So ADCs have metrics as well that allow you to evaluate them and decide what ADC you might want for your application. Probably most prominent of those is the ADC resolution. And ADC resolution is a little different from sensor resolution that we'll talk about. Sensor resolution is going to be the minimum detectable change in the output from that sensor. ADC resolution, you're looking at the possible number of output codes from that ADC. And that can be summed up by the number of bits. So for example, a 2-bit ADC would have 2 to the 2 or 4 output codes. And similarly, a 12-bit ADC would have 2 to the 12 or 4096 output codes. So the resolution of these two ADCs would be 2-bit and 12-bit respectively. Ultimately, the resolution is going to depend very heavily on the type of ADC, the actual kind of internal workings of that ADC. But typically, you're going to be looking at 8 to 24-bit ADCs available commercially. Another common metric for an ADC is the least significant bit of that ADC. And once again, that's a somewhat funny name for this particular metric because the least significant bit is actually a voltage. And it's the minimum voltage that's required to change the output code by 1 bit. So that would mean I have a voltage at my input that changes my output code for a 2-bit ADC, for example, from 01 to 10. It's increased it by 1 bit. Or if I had a 4-bit ADC going from 1011 to 1100, right? I've added a bit. I've increased that voltage just enough to uptick me 1 code. So that least significant bit, that voltage that we are calling a least significant bit confusingly, is going to be dependent both on the full scale range of my ADC as well as the number of bits. So if I had, for example, my 2-bit ADC with a 4-volt full scale range, I'm looking at a least significant bit of 1 volt in that case. Now, if I had something more impressive like that 12-bit ADC, I'm looking at a least significant bit voltage of approximately a millivolt. And so that means that if I increase the voltage at the input to my ADC, so say a voltage from a sensor, for example, if that goes up by a millivolt, my code at the output of the ADC will go up by 1 bit. Now obviously there are a lot of other metrics that you care about if you're trying to find an ADC for your particular application as well. And to look at those, you'd really go look at the datasheet of the ADC. So in this case, this is an ADS 1250. It's a TI ADC. If I look at this datasheet, I see it's a 20-bit ADC. It's a sigma delta ADC, which is one of the reasons it has that very high resolution. But I started noticing some interesting things, even if I just start looking at the first couple bullet points on this. Right? The second bullet point is particularly interesting because what it tells me is that even though they've labeled this a 20-bit ADC, and it is technically a 20-bit ADC, I really only get 18 bits of effective resolution at a given sample rate. So at sample rates up to 25 kilohertz, I get a full, in this case full, 18 bits of effective resolution on this ADC. And this highlights another thing of a sampling rate. So sampling frequency is another big metric that I might be interested in for an ADC, and we'll see why in a little bit. If I need to sample a signal at a particular rate, a particularly fast rate, I need to find an ADC that's up for that job, and 25 kilohertz isn't really that fast in the big scheme of things. Another thing we're going to care a lot about is the errors that my ADC might have. And we already talked a little bit about quantization error because we are dividing up the kind of output voltages that I have available to me with these discrete output codes. I have something called quantization error. And a basic way of looking at that quantization error is that in an ideal case, the voltage that I reconstruct from the code that I get at the output, so V in star, is going to be my code divided by total possible number of codes times that full scale range of the ADC. That will give me an approximation of the voltage at my input. And in an ideal world, that would be equal to my input voltage. But obviously that is definitely not the case. So a very simple example of that, if I have that 2-bit ADC that I've been using as an example throughout, I have 1.1 volt would map to a code of 0, 1, 1.2 volts would map to a code of 0, 1. Both of these, if I compute what that Vn star would be, both of these would give me an approximation of my input voltage of 1 volt, which is obviously quite different from 1.1 volt or 1.2 volt. So the quantization error, or often as we write it, EQ, is going to result from this grouping of input voltages and mapping them to single output codes in an ADC. And there are a number of consequences of this relative to the metrics that we just talked about for the ADC. First, it's dependent on resolution. The more bits I have, as M goes up, my quantization error is going to go down because I can better approximate. I have more of those horizontal lines. I can better approximate my input voltage. Another result from this is that quantization error is going to span one LSB, and remember LSB is a voltage. So EQ is going to be bounded by plus or minus 1/2 of an LSB. And so if I calculate that LSB, that voltage, I can get some sense as to what that voltage error actually means for example, a sensor input voltage to my ADC. And finally, there's a lot of other errors that can creep in. And in fact, these can be more significant than the quantization error. The quantization error is kind of just a result of how we create the ADC. But I can also have a lot of other errors. I can have linearity errors, I can have offset and gain errors. And typically I'm looking at kind of plus or minus a couple LSB here. And in this case, this happens to be an ADC from a microcontroller, one of the TI MSP430 series microcontrollers. And I can see here that if I look at the total unadjusted error here, my typical error is going to be plus or minus 2 LSB, and my maximum error is going to be up to plus or minus 5 LSB, which can be quite significant in the grand scheme of things. If I look, for example, at this case, I have a full scale range of 3 volt, a 10-bit ADC. I get a least significant bit voltage of about 3 millivolts. And what that means is that plus or minus 5 LSB is equivalent to plus or minus approximately 15 millivolts, which can be quite significant depending on what you're trying to sense. And the main thing that I want to convey from this, and you can find all of this stuff in the datasheet of an ADC, is that you really need to look beyond the number of bits and the resolution of the ADC to determine how appropriate it is for your application.